So this is problem number 2 from the 1980 AP Physics C exam. And in part A, we have to draw the electric field lines between these two plates. Now, since the top plate in this capacitor it has a positive charge density and the bottom plate has a negative charge density, when we have a positive test charge in between these two plates, the positive test charge will go towards the plate that has a negative charge density. And so in this case, our electric field lines are going to be drawn from going from the top to the bottom. And they're evenly spaced out and evenly distributed because the plates have an equal charge density. In part B, we have to use Gauss's law in order to find the magnitude of the electric field that passes through this dashed rectangular box. Now, we know flux is only accounts for the E field that goes perpendicular through the Gaussian surface. And so there are only two faces in this box where the E field is parallel to the area vector, which is at the top and bottom. All the other four faces are not accounted for because the E field is normal to the area vector. And so now you have like two faces left. Now we can disregard the first face on top because we know that all the charge on the plate is all on the inner surface, and the top face's rectangular box is above that. So there's no charge, there's no charge or E field that passes through that point. So all we are left is with that last face on the bottom. And so by Gauss's law, we know that flux equals Q enclosed over epsilon naught, which is equal to E dot A, or EA cosine theta. And since the area vector and E field are parallel, we know that cosine theta equals 1, and so that's basically disregarded. And so we can say that the E field is equal to Q over epsilon naught A. And since we know that this plate is uniformly charged, we know that sigma equals Q over A. And now all we have to do is plug into our formula or equation over here, and we get that the magnitude of the E field equals sigma over epsilon naught. And that's our answer for part B. Now in part C, the question asks us, what happens to electric field when a dielectric is put inside a capacitor? Now, we know according to Gauss's law that the electric field is equal to Q enclosed over epsilon naught A. And we have epsilon naught here because this is inside a vacuum. But when you have a dielectric, this is replaced with K epsilon naught, where K is always greater than 1 when it is not in air. So K equals 1 in air, and it's greater than 1 when it's not air. And so we know that in a dielectric, the denominator will always be greater than the denominator when you have a vacuum. And so we can say that the electric field in a dielectric is less than the electric field without one because the permittivity increases in the denominator, causing a smaller E field value. And so the electric field is less than the electric field when there is no dielectric.